if we take as a starting point, we're going to combine our time-independent kinematic equation with Newton's second law and derive what's called the work kinetic energy theorem. So net force equals ma, so that means the acceleration is net force over mass. And if we plug that in over here, that's 2 F over m delta x equals b final squared minus b naught squared. All right. And then if we leave this here, this is sum of the forces times delta x equals, move the m and the half over. That gives us this. Just rearranging it. So this right here, sum of the forces times delta x. Now this is assuming we're in one dimension, so the acceleration is in the direction of motion. So we're assuming here force is in the direction of motion. We could change this to throw in the cosine theta if we needed to, but basically what this is saying is that the work done by the net force is equal to, and then this quantity is something you may recognize, but it's called kinetic energy. It's Ke final minus Ke initial. So whatever net force is doing work, this essentially says that a net force will change the kinetic energy of an object. The work done by the net force will change the kinetic energy of an object. We know already that a force would cause an acceleration, which would change velocity, and that in turn changes kinetic energy. So this is called our work kinetic energy theorem right here. This is the equation, and then you can write it as, this is the same thing, just written more compactly, but then you'd have to know what Ke and what Ke is. So this, as I said, kinetic energy is half mv squared. It has units of joules, just as work does, and its kinetic energy is commonly referred to as energy of motion. It's the energy that you have because you are moving. So work causes a change in kinetic energy. Kinetic energy is something an object has. Work is something done to an object. Okay. And the work kinetic energy theorem is going to let us solve some problems that we could do using kinematics. And so is the full work energy theorem when we get there. Yeah, so we can apply this to a lot of different problems to figure out the work done. We take a simple example. We can say something like a 1,200 kilogram car slows down from 17 meters per second to 12 meters per second. How much work is done on the car? And that's just a simple application of the formula. Okay, so we know work is force times distance. We don't care about that. We want to know work equals a change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv naught squared. Depending on what you're given, it's often helpful to factor this. So our work is, sometimes it's more useful to write the equation like this, especially when you're finding that work. So that's 1/2, 1,200, 17 squared minus 12 squared. And so we can easily see that the work done on the car is 87,000 joules. A lot of times we would use kilojoules for something that's big like that. Kilojoule is just 1,000 joules. So that's a simple application of the work kinetic energy theorem. And I can give you other problems that will, and you will see other problems that will fall into this, just applying this equation. Related to work kinetic energy theorem is whether a force is conservative or non-conservative. As you might guess from the name, a conservative force conserves something, while a non-conservative force does not. So conservative forces, they do work, but that energy is stored as potential energy, which we'll talk more about later. So what is conserved is what's called mechanical energy. And mechanical energy is kinetic plus potential. Non-conservative forces do not conserve mechanical energy. Another way of, let me say this, that gravity and spring forces are examples of conservative forces. Non-conservative forces, friction, contact forces, like when you push something or pull something, are non-conservative. Electromagnetic force is conservative, but we haven't really talked about electromagnetic force yet. Anyway, yeah. So basically, conservative lets you store the energy. So if you think about gravity, if you lift an object, say you take an object and you move it up to a higher position, you've done work on that object. If you then drop the box and let it fall back to its original position, it will take that work that you've done and it'll turn it back into kinetic energy as the box falls. So that work was stored as this gravitational potential, and it was ready it was able to regain that energy. Likewise, if you compress a spring, you are doing work on the object as you exert force against the spring, but that force is stored in the spring, and if you let it go, then it'll gain that back as kinetic energy. Another friction, like I said, is non-conservative. So if an object is moving along and friction is doing work on it, this friction energy is dissipated as heat. So when I say it doesn't conserve mechanical energy, I'm referring to the energy of the object. So the energy of the object in question is not conserved. Energy is conserved. Energy conservation is one of the fundamental laws of the universe as far as we can tell. So like when friction acts on an object, the energy of that object is not conserved. Energy is conserved because that energy is dissipated as heat, generally. Another way of thinking about conservative versus non-conservative is that conservative forces are the work done is path independent, whereas with non-conservative forces, the work done is path dependent. Okay, and to illustrate what I mean, let's think about an example. Let's say I have a box, and I lift this box from here to here. Okay, I move it up and over. Okay, let's say I go straight up and then straight over. Say that's how I get the box there. Okay, let's consider the work done by gravity. Okay, on this segment right here, the box is moving upward, gravity is going downward. We know that gravitational force is mass times gravity. The angle between them is 180, so that just puts a minus out front because cosine 180 is -1. And then, whatever that change in height is, that's the work done by gravity on that. This is part 1 of the path. On part 2, we've got mg cosine 90 because gravity is down and the displacement is to the right. So the work done is 0. Okay. Now let's say we go from here to there, straight line, going that way. The work done by gravity on path 3 is equal to the force of gravity times the cosine of the angle between them. Well, now our displacement is off an angle while gravity is still straight down. The angle between them is some angle. Let's say this is at a, or whatever angle, it doesn't matter, whatever angle theta this is, then the angle between them is this theta plus 90. Okay, and then the distance is that height, that delta y, that theta, so the sine of that theta is going to be delta y over the distance, right? So then the distance is delta y over sine theta. Okay. Cosine of theta plus 90, if we apply a trig identity there, this cosine of theta plus 90 is just equal to minus sine theta. So we've got mg negative sine theta over sine theta, and we still wind up with it minus mg delta y. A way of thinking about this conceptually is that, gravity is downward. So work done by gravity is only relevant to the vertical distance traveled. And we could do this for all sorts of paths. So with gravitational, work done by gravitational force, it doesn't matter how we get the box from here to here. We could follow any sort of strange path. All that matters are the two endpoints. Okay. Now, let's say we consider friction. Now let's say we're on the floor, and we've got a box on the floor. We've got some mu, we've got some weight for the box, and let's say we push it horizontally. Say we move the box to here. Okay. If we push it here and then here, on the work done by friction on path 1 is mu, assuming we're pushing horizontally, is mu k times the normal force would be equal to mg in this case, times, whatever that distance is. The work done by the force on path 2 is mu k mg times whatever that second distance is, negative. Both of these are negative because force of friction always opposes motion. If we take it diagonally, path 3, the work done by friction on path 3 equal to minus mu k mg. Now that distance is square root of d1 plus d2. It's the hypotenuse. So if we go on path 1 and 2, the total work done, adding those together, is minus mu k mg times d1 plus d2. Whereas here, it's mu k mg times root d1 plus d2. So the path matters for friction. Friction is a non-conservative force. For a conservative force, the work on a closed path is 0. That is, if you take something from a starting point and you move it and wind up back at the starting point, total work is 0. Oops. For a path-dependent force, work on a closed path is non-zero for a non-conservative force. Think about friction. If I move this all around, every step of the way friction is opposing me and doing negative work, and so there's negative work being done. Whereas with gravity, any upward motion will result in negative work being done by gravity, which will then be canceled out by a downward motion doing where gravity does positive work. So that's the distinction between conservative and non-conservative forces.